Have you ever wondered why molecules have specific shapes? Let's explore this together. So, molecules are not just random assemblies of atoms. They are meticulously arranged structures, where atoms are held together by covalent bonds. These bonds are formed when two atoms share a pair of electrons. Now imagine these electron pairs as tiny magnets. They repel each other and try to stay as far apart as possible. This need for space influences the shape of the molecule. This is where the concept of molecular geometry comes into play. Molecular geometry is the three-dimensional arrangement of atoms in a molecule. It gives us a snapshot of how the atoms are arranged and how they bond with each other. Understanding the geometry of covalent molecules helps us predict their behavior and properties, but there's more to this story. Ever heard of the VSEPR theory? It's a key player in determining the shape of molecules. Now, let's unfold this scientific acronym. VSEPR stands for valence shell electron pair repulsion. A mouthful, isn't it? But don't worry, it's not as complex as it sounds. This theory essentially says that electron pairs in a molecule's valence shell repel each other, and they try to get as far away from each other as possible. This repulsion between electron pairs causes the molecule to take on a specific shape. Imagine a room full of magnets, all trying to stay as far away from each other as possible. That's essentially what's happening at the molecular level. These electron pairs are like little magnets, repelling each other and causing the molecule to take on a certain shape. Now, there are two kinds of electron pairs we need to consider here: bonding pairs, which are shared between two atoms, and lone pairs, which belong to a single atom. Both of these play a crucial role in determining the shape of a molecule. The VSEPR theory helps us predict the shape of a molecule by looking at the number of bonding and lone pairs in its valence shell. For instance, if a molecule has two bonding pairs and no lone pairs, like in the case of BCl2, it will be linear. If a molecule has three bonding pairs and no lone pairs, like in BCl3, it will be trigonal planar, and so on. But here's a fun fact. Lone pairs take up more space than bonding pairs, causing even more repulsion. This means they can distort the shape of a molecule even further. So, the VSEPR theory helps us understand why molecules take on certain shapes, but how do these shapes come about? Let's dive deeper. Now, let's understand the process that allows these shapes to form: hybridization. Imagine you're a fashion designer. You have a collection of different fabrics, each with its own unique texture and pattern. To create a stunning outfit, you combine these diverse materials into one cohesive design. This is similar to how hybridization works in chemistry. Just as a designer blends various fabrics, atoms mix different types of orbitals, s, p, and d, to form hybrid orbitals. So, what exactly is hybridization? It's essentially a mixing of atomic orbitals of similar energies to produce new orbitals. These new orbitals are called hybrid orbitals because they are formed by hybridizing or combining different orbitals. Let's delve a little deeper. In an atom, the s, p, and d orbitals have different shapes and orientations. The s orbital is spherical, while p orbitals are dumbbell-shaped, and d orbitals are even more complex. When these orbitals hybridize, they adopt new shapes and orientations that allow atoms to form bonds in specific geometrical arrangements. For example, consider methane, a molecule with one carbon atom and four hydrogen atoms. The carbon atom undergoes VSEPR hybridization, meaning it combines its one s orbital and three p orbitals to create four sp3 hybrid orbitals. These orbitals arrange themselves in a tetrahedral shape, allowing the carbon atom to form bonds with the four hydrogen atoms. But hybridization doesn't just influence the shape of molecules, it also affects their properties. For instance, the strength, length, and energy of a bond can all be influenced by the type of hybridization involved. In essence, hybridization is a transformative process. Just as a fashion designer can create an entirely new look by combining different fabrics, atoms can create unique molecular structures and properties by combining different orbitals. Hybridization is like a molecular makeover, transforming the way molecules look and behave. But there's even more to molecule formation. Ready for a deeper dive into the world of molecules? Let's talk about the molecular orbital theory. Now you might be thinking, what is this molecular orbital theory? In simple terms, this theory allows us to understand how atoms combine to form molecules. It provides a qualitative description of the electronic structure of molecules, and more specifically, homonuclear diatomic molecules. These are molecules composed of only two atoms of the same element, like oxygen or nitrogen. Let's simplify this further. the molecular orbital theory is a bit like a molecular matchmaking service. It explains how atomic orbitals, the regions where you'll most likely find an electron in an atom, merge to form molecular orbitals. These molecular orbitals are the potential paths for electrons in a molecule. They can either be bonding, where electrons are most likely found between nuclei, or antibonding, where electrons are found outside the nuclei. The key point here is that molecular orbitals are formed from the combination of atomic orbitals, and the number of molecular orbitals formed is always equal to the number of atomic orbitals that combined. This helps us to understand the bonding in molecules. Take, for example, a hydrogen molecule, which is a homonuclear diatomic molecule. Each hydrogen atom has one electron in its atomic orbital. When two hydrogen atoms combine to form a molecule, their atomic orbitals merge to form one bonding molecular orbital, where the two electrons reside. This is the basis of the bond formation in a hydrogen molecule. But remember, this is a qualitative idea of the molecular orbital theory. It has its complexities, with various factors influencing the formation and nature of molecular orbitals. But for now, this basic understanding should help you appreciate the intricate workings of atoms and molecules. Molecular orbital theory, though complex, gives us a deeper understanding of molecule formation. And speaking of bonds, there's one more bond we should talk about. Let's end our journey with a special kind of bond, the hydrogen bond. This is not your everyday kind of bond. It's a weak attractive force between a hydrogen atom, which is covalently bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine, and another electronegative atom in a different molecule. But don't let its weakness fool you. This bond has some impressive properties. For instance, it's the very bond that gives water its unique structure, allowing it to exist as a liquid at a room temperature. It's also the reason why we have DNA, as hydrogen bonds hold the two strands of the DNA helix together. Now, isn't that something? The smallest of bonds playing such a huge role in our world. So, the next time you sip your water or look at a model of DNA, remember the humble hydrogen bond. So, there you have it, a crash course on the geometry and bonding of molecules. Quite a journey, wasn't it? We've covered a lot of ground today, haven't we? From the intriguing geometry of covalent molecules, to the fascinating VSEPR theory, to the complex concept of hybridization involving s, p, and d orbitals, we've journeyed through the captivating world of molecular structures. We delved into the molecular orbital theory of homonuclear diatomic molecules and wrapped up with an in-depth look at the power of hydrogen bonds. But the learning doesn't stop here. We'd love to hear your thoughts and queries. Do you have any questions about what we discussed today, or perhaps there are other topics you're eager to learn about? Please share your thoughts in the comments section below. Engage with us, and let's make learning an interactive and fun process. Remember, curiosity is the engine of achievement. Thank you for watching. Don't forget to like, share, and subscribe to Facts Academy 0122. Stay curious, keep learning.